Good morning. I'm glad you all made it despite the weather and trouble with the trains. Dear fellow physicists, it is with great pride and pleasure that I open this edition of the Physics at FOM conference. Physics in the Netherlands is thriving, and measured by impact, we rank first in the world, before countries like the USA, Switzerland, and Denmark. In the physics world list that came out in January or December, 10 of the 10 most important discoveries, physics discoveries of last year, 2 were done by you. And on top of that, you took a relatively large part in the third, the discovery of the Higgs, the particle that must explain your massive presence here. Being together with 1,900 representatives of Dutch physics research, you may not immediately realize this, but you are an endangered species. The Dutch government underspends on science, but especially physics is relatively small, only 0.6% of the world average on spending on sciences. We are small compared to physics in other countries around us. We are small compared to the world average. In size, that is. Quality is important, but size matters too. In the world of science and humanities, Dutch physics is like food in a fancy restaurant. It's very good, but there's so little of it. Our statistics may be unbeatable. We may win all the competitions, score aces in the ERC, have the highest impact in the world, carry home scores of important international prizes, but somehow we do not succeed in getting across the message that physics, apart from being interesting and highly intellectually stimulating, is really important for society in so many ways. And very, very often, it's useful too, in the short term or the long term. Now look at us. Here we are, 1,900 souls tuned to a secret wavelength, discussing alien concepts very few people can grasp in an hermetic language that no normal person understands or even recognizes as the carrier of information, let alone emotion. Emotion, which is the principal currency in today's world. No wonder we are under-recognized and underfunded. But all of that is changing. Following in the footsteps of Robert Dijkgraaf, who dazzled the TV audiences with his live lectures in De Wereld Draait Door, other physicists, other scientists, researchers appear in talk shows. Leo, of course, showing how Duplo bricks can be used to construct the Majorana fermion. And the Higgs discovery was opening news on the Dutch television. But others appear on the talk shows too. Young people, enthusiastic people, people with hair. And we need a lot of that. Following up on an initiative of 2 young researchers, Ivo van Vulpen and Egge van der Poel, FOM has organized a competition in which young researchers were invited to do a 2-minute movie about their research, with outstanding results that you can see at this conference on the video columns in the central hall near the posters. 3 winners were selected. Fei Pei of Delft University, Hannes Bernien, also from Delft, and Laurens van Dijk from Utrecht. The winners were awarded with a portrait, a video portrait, that is, of them and their work, and those 2 are on display. And a special mention was given for perhaps the most unusual, daring, and artistic film of all, by Rianne uit Hoen, who danced her PhD project, which she carries out at the Differ Institute. She definitely dares to differ. In this opening address, I do not intend to spend much time on political stuff. But you all know that science funding in this country is fundamentally changing, which causes dynamism and uncertainty, threats and opportunities in spades, topsectoren. It's easy to see those developments as threats, as a monster that threatens science, and physics in particular. But then, not so long ago, I spoke to a little boy who had had a nightmare in which he was chased by a monster. He ran and ran as fast as his short legs would carry him, but the monster was soon upon him, and his legs gave way. There he was on his back, helpless and panting. He asked the monster, "Monster, what are you going to do to me?" Upon which the monster says, "How should I know, boy? It's your dream, not mine." Let me just say that we in the FOM board do spend quite some time discussing budget things, which is necessary, but not inspiring. But we, and more in particular, Wim van Saarloos, the FOM director, and Hendrik van Vuur and Job de Kleuver, and the entire team at FOM, spend a lot of time and effort developing new opportunities, such as new ways to work with industry. That is inspiring. It's not easy, finding new roads never is, but you meet new people, you get to see new sites, you get influence. Let me end by saying this: you're the best in the world, the pinnacle of evolution, yet you're an endangered species. What can I say? Go forth and multiply may not be the best advice. Go forth and communicate may be more appropriate in this case. In any event, at this conference, get inspired, inspire others, cross-fertilize, jump over fences, bridge gaps, meet people you didn't know, make new friends, clash with other cultures, forget about categories, about boundaries, fundamental, applied, bottom-up, curiosity-driven, use-inspired, theoretical, experimental, forget all those barriers, and use this conference to sample lots and lots of excellent physics. Be curious, be inspired, charge up your batteries, and have fun. It's your party, not mine. Thank you. Then I should like... Thank you. Then I should like to invite Tony Donnet to the podium to introduce our first speaker.
Good morning, ladies and gentlemen. It's a real pleasure for me to announce the first keynote lecturer of this conference, Sibylle Günter, from the Max Planck Institute in Germany. Sibylle was born in Rostock, in former German Democratic Republic. She did her studies there at the University of Rostock in physics. She finished her PhD in 3 years, so maybe a good lesson for our PhD students, which we try to keep in 4 years. And the topic of her thesis was focused on computational investigation of radiation from dense plasmas, and it was in the Department of Theoretical Physics. Subsequently, she stayed as scientific advisor or scientific assistant to the chair of the theoretical department, and during that time she had some extended stays to the University of Maryland and to the National Institute of Standards and Technology. In 1996, she basically wrote her super thesis, her Habilitation, as they call it in Germany, on a thesis entitled Optical Properties of Dense Plasmas. And since that time, she is giving lectures at the University of Rostock, where in 2001 she became adjunct professor. In 1996, she also made a move to the Max Planck Institute for Plasma Physique in Garching, near Munich, where she became staff member. And in 2000, she became head of the Tokamak Physics Division. More recently, 2 years ago, she became the principal director, the scientific director of the Institute for Plasma Physique, which is by far the largest fusion research institute in Europe, with two big laboratories, one in Garching near Munich and the other one is in Greifswald, somewhere between Berlin and Hamburg, near the Ostsee. In 2006, he also became honorary professor or part-time professor at the Technical University of Munich. Well, there's a lot to say about Sibylle, and I will not repeat all because otherwise she doesn't have time to give this lecture here. I could, let's say, finalize by saying that she is also at this moment chair of the EFTA steering committee. EFTA, that's the European Fusion Development Agreement, that's the association of all fusion institutes in Europe. And she has a very important role there. Well, through her, let's say, entire professional life, she worked on many topics, most of them, let's say, related to the theory. And, well, she will certainly address a number of them in her talk, which hopefully will give you a kind of idea that fusion is not all about building, let's say, new reactors for the future, but there's also a lot of fundamental physics in there. And so I'm looking forward to your talk, Sibylle. The floor is yours.
Good morning, ladies and gentlemen. Thank you, Tony. I'm very honored to give the first plenary talk here at your very important conference. And it's a pleasure to talk about recent advances in magnetic fusion research, and also at the very end about the perspectives of magnetic fusion research to contribute to the energy mix in the second half of the century. For introduction, however, I would like to start with the fusion reactions we are looking at. Well, you well know, in contrast to fission power stations, we are trying to fuse light nuclei into heavy ones, in particular the heavy hydrogen isotopes, deuterium and tritium, to helium. And the energy gain is, of course, due to the dependence of the binding energy per nucleon with mass. We do not choose the same reaction as we have in the Sun, where directly 4 protons are fused to helium. And the reason one sees, if one has a look at the reaction rates here, so 4 protons are essentially fused to helium in 3 subsequent reactions. And the reaction that matters most is the first one, 2 protons fused to deuterium. And here the weak interaction is involved, and therefore the fusion rates are quite slow. And well, as we are not going for a sun-sized fusion reactor, we better go for a more efficient reaction. And therefore we have chosen deuterium and tritium, where the fusion reaction rate is 27 orders of magnitude larger. Well, deuterium is easily available worldwide, so it's contained in seawater to 0.015%, so you can easily have this fuel nearly unlimited and everywhere. This is not true for tritium, I will come to that later, but the 2 fuse to helium and a neutron is set free with an energy gain of 17.6 mega-electron-volt per reaction. So tritium is radioactive and has a half-time of about 12 years. So we have to create this tritium ourselves in a fusion power plant. And for this we can use the neutron that can breed out of lithium-6, tritium and helium with another energy gain. Well, there are essentially 2 ways to fusion power plants. One is inertial fusion and the other is magnetic fusion. For both, we need to achieve about 150 million degrees temperatures to have sufficiently high fusion rates. And this is quite a high temperature. It's about 10 times larger than the temperature in the solar interior. Well, for inertial fusion, you take a very small pellet with frozen deuterium and tritium, and you surround it by some heavy metal, and then you have many lasers to compress it, and you actually create a mini explosion. But the inertia of the matter is sufficient to keep it sufficiently long together, about 10 to the minus 10 seconds. It's sufficient to have sufficient fusion rates to have a positive power balance. I won't go into detail of that research, and the reason is this is being done mainly in the US and Japan. There's some laser-driven plasma physics probably also in the Netherlands and in other European countries. But we only have some heat and touch activities in Europe for laser fusion, which is in the US, for example, nearly entirely financed by military, and the reason is this has military applications. In particular, you can test your computer codes for nuclear weapons very cheaply, well, not very cheaply, but relatively cheaply, and without too much radioactive waste. So therefore, I will concentrate on magnetic fusion, where you use the fact that at these temperatures, matter is, at least hydrogen, is completely ionized, and you deal with plasmas that can be influenced by magnetic fields, and you can confine the plasma by the means of magnetic fields. And in contrast to the inertial fusion, where you need very high densities and you end up with pressures comparable to the solar interior pressure, the pressures here are very small because the density we need to achieve is about a factor of 1,000,000 smaller than the particle density in the atmosphere. And therefore, the pressure is about 10 atmospheres, despite the very high temperatures of 150 million degrees. And on the other hand, we can keep, of course, the plasma much longer together than 10 to the minus 10 seconds. Well, you well know particles can move freely only along magnetic field lines, and the Lorentz force forces them on a circular motion around the magnetic field lines. If you want to build a magnetic device, a magnetic field cage, you better avoid that particles can leave the field cage along magnetic field lines, and this calls for a torus. So you can prove that just toroidal field lines don't do the job, but you need to have a structure where magnetic field lines trace out so-called magnetic surfaces. So you have, if you start a magnetic field line here, it turns around the torus, it has to end up on such a surface, and then the whole device is constructed out of nested magnetic surfaces. And as the transport along magnetic field lines is far faster than perpendicular, and at these temperatures, for example, the heat transport is 10 orders of magnitude larger parallel than perpendicular, you end up with nearly constant temperature and density on these surfaces, and this gives you a very good heat insulation. In fact, we need a heat insulation here that is about 50 times larger than that of polystyrene at these high temperatures. But having said that, on the other hand then, we have very low power densities in these devices. So we have about 100 times less power density than in a car engine or in fission reactors. Well, there are essentially two ways of building a fusion power plant. One is the so-called tokamak, where you create these magnetic field structure with the nested magnetic surfaces by two components. You have so-called magnetic field coils, and if you have a current flowing in these coils, then this is associated, of course, with this toroidal magnetic field lines here, sketched by these green field lines. But in addition, you use the plasma as a secondary winding of a transformer, and you induce a plasma current, indicated by these red arrows here. And this plasma current, of course, comes with a poloidal magnetic field line, with these field lines. So if you combine the two, you end up with the black field lines, and this is exactly these magnetic field lines that trace out magnetic surfaces. Well, this is the simplest fusion device you can think of, at least a toroidal device. It has an exact or nearly exact axisymmetry, and therefore you have really nicely intact magnetic surfaces. You can prove that in such an axisymmetric device, charged particles, unless they are disturbed by collisions, these orbits close in itself, so they would never leave the device. So this comes with a very good heat insulation due to the exact symmetry. On the other hand, as you've just said, we need to induce a current on the plasma. This, of course, allows for pulsed operation only. And the current flowing here is a source of free energy, and therefore is able to drive instabilities that can even destroy this magnetic field structure. The alternative doesn't have these disadvantages. The stellarator is able to produce the whole magnetic field structure by external fields only, by external magnetic field coils only. There's no plasma current needed for a stellarator, and so you have the opportunity for full steady-state operation. And you get rid of the plasma current, and therefore this device is more stable against perturbations. On the other hand, everything comes with a price. There's no free lunch. You have to give up for that advantages. You have to give up the exact symmetry. You can prove that you cannot have nested magnetic surfaces without a plasma current in two-dimensional geometry. This three-dimensional geometry in general comes then with much poorer heat insulation, and also particles now can leave the device even if they are not disturbed by collisions. I will come to that later. In the recent decades of research, the two concepts have been further developed, and for the tokamak operation, it has been found that by using external means of current drive, so essentially by waves, but also using intrinsic currents that are driven by thermoelectric effects from the pressure gradient you just keep up by heating, then you can replace a large part of this plasma current by intrinsic or externally driven currents. So this finally allows you to go at least to very long pulses, if not steady state. You should remember here our plasmas are very hot and very thin, and therefore there are not many Coulomb collisions, so the resistivity is very small. You can drive mega amperes of current with millivolts. So therefore, this can go for very long pulses. And we have developed very sophisticated feedback systems such that we are able to actively control these instabilities and safely operate our devices. Well, for stellarators, there has been the invention of so-called quasi-symmetries. So while you can prove mathematically that the whole magnetic field cannot be axisymmetric, there can be symmetry properties of the magnitude of the magnetic field. And if you use that, you can get rid of the disadvantage. You can really end up with good thermal insulation, and you can end up with closed particle orbits, unperturbed particle orbits. So if you want to summarize the success of about 5 decades of research, this can be done in this kind of a diagram where the x-axis gives you the temperature, and the y-axis gives you our figure of merit, which actually results from the power balance between the heating by the alpha particles of our plasmas versus energy losses. So this is plasma density times temperature times the measure of the quality of our heat insulation. Well, already the very first tokamaks in the former Soviet Union were able to reach temperatures of a few million degrees. People have thought that it would be very hard to heat up plasmas to temperatures 10 times higher than the solar interior, but actually this was quite well possible, so we have even exceeded those temperatures by far. You see we have reached 400 or 500 million degrees. We also increased our figure of merit by a factor of 10 to the 5th, but there's still a factor of 5 to 10 missing, and this is missing heat insulation. So we need still further to improve our heat insulation, and this we are going to do by increasing the size of the device, and I will come to the next step, experiment ITER. Well, all the black points here are tokamaks, and the blue points are stellarators. And while the first tokamak was really a success, the first stellarator was a disaster. So the first stellarator didn't work at all, and then therefore the world nearly switched to tokamaks. There are now some stellarators around worldwide. Here you see actually 3 data points from stellarators, and you see that these are very much behind the tokamaks. And the reason for that is that, as I said, stellarators need optimization, quasi-symmetry is important, and to do that, you need high-performance computers. At least, not present-day high-performance computers, but some computer power, and this was only available in the 1980s. And so the stellarator is lagging very much behind the tokamak. Tony has said we have an institute also in Greifswald, and there we are building up the presently largest and most innovative stellarator, Wendelstein 7X, and this is a parameter space we hope to reach there. Well, actually, there are many jokes around, of course, that fusion has been taken forever and that is the energy source of the future and will always be. If we, however, really compare our figure of merit with other fields, it doesn't look that bad. Also, it has caveats, I will come to that. But if you compare our figure of merit, for example, with the development of computer chips, we are not doing that badly. So at least till 2000, our success parameter doubled every 2 years as well. Similar things are true for high energy physics. But there's one major difference between high energy physics, fusion, and the computer chips. We needed bigger devices, both of our fields, to go for success, while the computer chips decreased in size. Well, this wouldn't be sufficient to say, well, fusion never progressed. I think the major obstacle is that fusion needs to increase above a certain threshold, and unless we do so, we still waste energy rather than produce it. And so we can consider success only if we gain more energy out of fusion reactions than we need to heat up our plasmas. And that's probably the reason why, despite the huge progress in achieving parameters, fusion is still considered, not yet at least, to be successful. Well, we want to cross this threshold with the next step experiment, ITER, that is currently being built in South France, in Cadarache, and I will come to that. First, I would like to give now some examples of tokamak research. Well, there are plenty of tokamaks around worldwide, and I'm showing the largest here only. The largest at the moment is located in Culham, UK, the Joint European Torus. This is the largest experiment worldwide, and it's a joint experiment for all European laboratories. So also many Dutch physicists are going for JET and doing great research there. So ITER is expected to be a factor of 2 larger in linear dimensions. Well, a factor of 2 smaller in linear dimensions is our experiment in Garching, Aztecs upgrade. And there are several tokamaks of that size in the world. One is located in California in the US. And there are plenty of new devices, superconducting devices even, in Asia. Tokamak East, very similar in size to Aztecs upgrade. And also a superconducting tokamak in South Korea, K-Star. And there's another tokamak being built up at the moment of the JET class, GT60SA. And this is a collaborative tokamak that is being built in collaboration between Europe and US. Europe and Japan, of course. It's going to be built in Naka, in Japan. Well, those of you who are experienced in high particle physics would now say, well, why not go just for the biggest machine and forget everything else? Well, this is not wise, as we can use our smaller experiments in kind of wind tunnel experiments towards the bigger ones. There's one thing you have to acknowledge there. You need to have the same magnetic field geometry, and then you can do some wind tunnel experiments. You see here, again, our nicely nested magnetic surfaces, which I've said in the beginning, this is needed to have a good heat insulation. But then you see here as well that there's a last closed flux surface, and that one touches a wall, and it's the only magnetic surface or the only field lines that field the plasma and the walls, so you can really concentrate the plasma wall interaction into this chamber called diverter here. And this development was very successful, has been initiated in Garching at our institute, and then brought to JET, that has been modified accordingly, and now the ITER design looks very much the same. We don't need to prove that the deuterium-tritium fusion reaction works. This has been done at the US tokamak TFTR and later at JET, and we have been able to produce 16 megawatt of fusion power already. at jet, with this slight caveat that still we needed more heating power to heat up the plasma than we got out of it, but it was not by a large margin. It was just 60% of the heating power we needed for plasma heating we got out by fusion reaction. But we still, of course, need to do better, and this is planned for ITER, where we want to exceed the heating power needed for plasma heating by a factor of 10, at least. So this is the dimensions of the machine. The major radius is about 6 meters. This is very close then to reactor size already, where people now think of 8 meters. Plasma radius is 2 meters. We have a plasma current of 15 megaamperes, magnetic fields of 5 Tesla. And with this machine, we are aiming at fusion powers between 400 and 800 megawatts for about 400 seconds to a pulse duration of about an hour. As I said, this machine is being built in South France, in Cadarache. And there are 7 partners to this project. The European Union counts as one partner, which is not always easy, with 27 member states: China, India, Japan, South Korea, Russia, and the US. While, of course, the scientific project and the design of ITER is an outcome of the discussions of the scientific community. But in this particular project, the politics has played a major part here. This project has been announced by Reagan and Gorbachev when they wanted to show the Cold War was over. And so they said, well, let's go for a peaceful project, a peaceful usage of nuclear power again, this time fusion. Well, this was, of course, a great idea. You have 7 partners, half of the people living around the world, and 80% of the gross income of these countries. But this came with a caveat. I mean, they had even greater ideas, saying every of these partners should be able to build a fusion power plant afterwards, and therefore should be allowed to learn every single technology. This is a very good idea in principle, but this means then everybody should have the possibility to build, for example, a magnetic field coil or something like that. And this then led to very broad distribution of tasks. And this reminds me always, if you develop a new car, right? You decide you develop one wheel in US and one in Japan, one in China and one in Europe, and then you bring them all together, and then you have had all the development and research costs. You hope it fits together. So I just want to tell you, this is a very, very complex management task. In addition, there's not the money with the central management, but with the domestic agency, so with the partners, and they bring everything in kind. And if you have read in the newspapers that ITER was lacking behind schedule and the budget was not as planned, this is not the only reason, of course, but it's part of the reason. Still, it's going on. So this is the ITER site. They have finished a few buildings already. So this is a building to wind up the largest coils you cannot transport anymore. The administration building, of course, is done, but also the tokamak building is being built. So this is the pits to make it safe against earthquakes. And by middle of last year, the ITER organization has committed 80% of the in-kind values. The licensing is nearly completed. More than 70% of the superconducting cables for the magnetic field coils, the major element of the device, is produced. And we expect the first hardware to be delivered to Cadarache in next year. Well, Tony has said it's not all about building big devices, it's also about science and plasma physics. And I want to give you some overview here. First, I would like to show you what is the physics we are dealing with about. And so fusion plasma physics is a truly multi-scale problem, both in space and time. The smallest scales we have to resolve is the gyration radius of the electron, and this is less than a millimeter. The largest scale is the device size. For ITER, this is 2 meters. In time, well, actually, we would have to resolve even the fast gyration time, but usually you can average this out. But you have to look at time scales for the major plasma waves, the Alfvén waves, once around the torus. Then you have the transit time of the ions, and then you see that ions transit many, many times around the torus before they once collide. And this means, actually, we have to deal with a kinetic description of the plasma, because the particles don't collide often enough that you can use fluid pictures. On the other hand, we can still talk about temperatures, what I did all the time, because the particles do stay on a magnetic surface for long enough to have many, many collisions before they drift away. And the largest time we have to deal with is the time of the resistive redistribution of the current profile, and this is of the order of several tens of seconds. So to deal with all these time scales, of course, we have developed several physics models. So for the larger scale, it's still okay to deal with some transport equations. For larger scale instabilities, we look at extended fluid models. But if you want to really go from first principle theory, you have to deal with kinetics. And as I already said, we try to average out the fast gyration motion. So we replace the motion perpendicular to the magnetic field by kind of the motion of charged rings. One of the major problems we want to deal with to really predict the necessary size and the properties of a fusion power plant is turbulent transport. And if you look at the history of the turbulent transport, as the transport at all, then you see why people had made promises they were not able to keep at the very beginning. If you think of a thin, high-temperature fusion plasma, and you take a tokamak where the particle orbits are closed in itself, then you hardly find any effect that could lead to particle diffusion except collisions. But collisions are very rare, so the high temperatures actually prevent mainly collisions. So if you estimate then now the transport induced by collisions, you take a simple estimate, take a particle orbit. Here I took the gyration radius. This is not perfect, but take any particle orbit size as the length scale for diffusion coefficient, and then the time in between two collisions as a time scale. And then you end up with very, very small diffusion coefficients. And you would come to the conclusion that you could have your fusion power plant basically in the basement. Well, this didn't work out, actually. Instead of 10 to the minus 2 square meter per second, we find a few square meter per second transport. And then you come to the conclusion that tokamaks would ignite at a major radius of 8 meters only. But the reason for that is that we do not only have this collisional transport, so it's not a single particle picture that is sufficient. We see that we have turbulent fluctuations on both plasma density and temperature. And if you now would make such a simple estimate, you take the size of the turbulent eddies as the length scale and the tearing time of these eddies as a time scale, then you would end up with the right order of magnitude. Those of you who are working in fluid dynamics know very well that the turbulence problem is one of the last unsolved problems of classical physics. And therefore, our devices usually were based on simple empirical scaling laws. And this is how this looks like. This is a measure of the heat insulation at many, many tokamak experiments, and versus a scaling law that involves size, magnetic field, plasma current, and all these engineering parameters. And then you see, at least in a double logarithmic plot, these data points line up very nicely, and then you extrapolate to eta. And I'm quite confident this will work out, as the parameter range you need to extrapolate is about the same size as you can really reach within one experiment. But still, if you want to go for a fusion power plant, if you want to know exactly what's going on, if you want to predict things, actually you rather would like to know the physics principles. So I would like to know, if you give me the heating power for such a plasma, I would like to be able to predict the temperature profile. Or same with particles and the density profile, and so on. So then, however, we need really a first principle description of the problem. So we need to start from ab initio physics models, and I already told you what we have to do. We have to start with a gyrokinetic theory here. And this you don't solve with a pencil and a sheet of paper. You need high-performance computing for that. So in principle, how this works is we drive turbulence by heat input, but first, of course, heat input increases the pressure gradient. This then initiates and drives turbulence. The turbulence leads to diffusion that finally determines the pressure gradients. Well, we have some particular ingredients in our fusion plasmas. I've already shown you that ions, for example, travel many times around the torus before they once collide. So they do feel the magnetic geometry. So you cannot just have a simple mock-up model, you really have to involve the whole geometry. In particular because our transport is very anisotrope. So I already told you that, the parallel heat conduction is a factor of 10 orders of magnitude larger than perpendicular. And so you have to involve this, and this is computationally a big problem, and we have to include kinetic effects. Well, this is a simulation of turbulent transport for a present-day tokamak experiment, and you see this mixing up in temperatures here very nicely. And if you try to understand, again, why people have not understood from the very beginning that turbulence transport was important, you see that before we were able to develop efficient heating schemes, turbulent transport didn't occur, because there's a critical gradient before turbulent transport sets in, and below that, you don't see it. But once you reach this critical gradient, you're not able to exceed it, so you can heat and heat and heat. The temperature gradient would not increase. You have kind of stiff temperature profiles. And if you give me the temperature here, I can predict the temperature there. This is not true for the very edge, as you see. I will come to that, and not for the very center, where we have some instabilities occurring and flattening the profiles. So this is the logarithmic plot for the electron temperature. You see very self-similar profiles here, and there's a kind of transport barrier at the edge. And this temperature at the plasma edge you can determine by the specific particular geometry of the outer flux surfaces. And to understand these transport barriers, you have to look at the saturation mechanism for the turbulence, and this is due to sheared flows. And sheared plasma flows deform turbulent eddies or tear them apart, and this reduces the turbulent transport. And this, for example, brings you here then a transport barrier at the very edge. And this was discovered for the first time then in Garching, and now this is the operational scenario for ITER. But if you learn a lot of things about turbulence, and if you really go into detail, then you can really get such transport barriers also in the plasma center. And here you see we have reached even ignition temperatures, so 200 million degrees, in a device with a plasma radius of this size, 50 centimeters. Here you have 200 million degrees, here you have 1,000. So this is one of the topics, and another very important topic will be come with ITER. This is a thermonuclear self-heating of the plasmas by the alpha particles. Well, if you first look at the particle orbits, then you can see that the particles do not simply follow magnetic field lines. They have drifts, and because every force perpendicular to magnetic field lines causes a drift perpendicular to the force and to the magnetic field. And in addition, you have this pseudo-periodical motion, which comes with a constant of motion, that is the magnetic moment, and it's a ratio between the perpendicular energy divided by the magnetic field. So this you can look at particles moving in the Earth's magnetic field. So the particle goes along magnetic field line, it comes to in regions of higher magnetic field strength, then it has to increase perpendicular energy, but as the energy is of course conserved, this goes then with a reduction of the parallel energy, and if the parallel energy is not sufficient, these particles will be reflected. But this is very similar to our tokamak geometry. A toroidal magnetic field is not homogeneous. It falls off like 1 over r from the center to the edge. And then if you follow a particle that doesn't have enough parallel energy in a tokamak, you see this looks like this. You start the particle here. It tries to go once around the torus, but it will be reflected in the region of high magnetic fields. And if you then look at the projection, you see that the particle orbit deviates from the particular surface, but the particle orbits are closed. And we will see this is very different to stellar-raters. Well, if we go for more details, then we also see that it's not only particle orbits, it's also that alpha particles have a similar velocity like the characteristic wave velocity, the alphane waves, and so they can resonantly interact with them and exchange energy. So of course you have more energetic particles in the center than at the edge, so they have a radial gradient. And this radial gradient is a source of free energy. It drives waves, which in turn then lead to a redistribution of energetic particles, flattening this distribution function. And that way you move alpha particles from the core towards the edge, and you even can expel them. And this might be dangerous for the walls. And therefore we have a look at this at the moment as well. So we have specific diagnostics to look at loss of fast particles. This is of course not alpha particles, but we do use fast particles for heating. And you see here these particle losses at a certain frequency, well in line with the corresponding magnetic fluctuations. And now this is a point where theory matters, so you want to understand the instabilities you observe in your devices, and then if you have checked your theory, then you are confident that you can predict for ITER as well. And here you see nicely a theory plot for the perturbation of the electron temperature compared with a corresponding experiment, and this experiment diagnostic has been developed, and the experiment is carried out on our Tokamak SX upgrade by our colleagues from the DIFA Institute, so we have a nice collaboration here. And so this is very important to predict then the ITER performance with respect to fast particles. I have 35 on my screen. So stellar-raters, there are much less stellar-raters around than tokamaks. So actually there are two at the moment, a small one in Spain and another one in the US. This one has been shut down already because we wanted to build up Wendelstein 7X. There's a major leading device now in Japan, but this one is not an optimized stellar-rater. And what this means, I'll show you on the next slide. Here you see the coil structure of a stellar-rater. You have these field coils for the toroidal field, and then these helical windings around the plasma to compensate for the plasma current. The problem is that in general 3D, particles can really drift in radial direction out of the torus. And this you have to avoid, and that we did carefully for the coil systems of W7X. If you look again at this coil system, you see now the difference. We do not have two separate coil systems. We have these dark blue coils, which is this is non-planar coils, and this is a discrete coil set that does actually the very same as the two coils. The light blue coils here are just for having some experimental freedom. And then you look at the magnetic field structure. You see it's a pentagon, and you have regions of high magnetic fields in yellow and red, and low magnetic fields in blue. And so particles that are now trapped between these two regions of strong magnetic fields really are in danger for being lost. But if you now zoom into one of these 5 modules, then we see that the motion of the particles for this optimized field structure is not completely along magnetic field lines, but within a magnetic surface. So the particle cannot drift out of the stellar-rater. And so we expect a much better confinement for this stellar-rater. Well, if you look at the device now, we have a major radius of 5 meters, a minor radius of 0.5 meters. It's a superconducting device with 30 cubic meters of plasma volume and a large cold mass. So we have 50 of these non-planar coils. We aim at a magnetic field of 3 Tesla and a pulse length of 30 minutes. Well, the next pictures just show you some these are some pictures from assembly. So this is the magnetic field coil. This is one complete module. The vacuum vessel usually reminds you always Swiss cheese, but this is for curiosity of physicists and heating methods and all the pipes. And here you have then the whole torus assembled. So you might wonder, why do we need 2 concepts? Well, out of several magnetic confinement concepts, many have been investigated. It's tokamak and stellar-raters that remained. The tokamak shows a very good performance, but you need a careful feedback control, and continuous operation is still an issue of research. On the other hand, the stellarator can really operate continuously, but we have to show first that it really can reach the full tokamak performance. It needs optimization. It's more difficult to build. Hopefully, we will see easier to operate. In any case, for fusion research, ITER is the right next step, because on the one hand, the stellarator build-up now supports the ITER assembly. On the other hand, everything you learn in ITER technology, you can also use for stellarators. Well, if you now look at our way towards a fusion power plant, while we are building up ITER, in parallel we deal with tokamak and stellarator research. Wendelstein 7X will go into operation in 2014. We have material developments and technology developments. We plan for DT operation and demonstration that fusion really can gain more energy than put in for plasma heating in 2027. And if we then start to design a demonstration power plant, we are confident that we will be ready with such a power plant before 2050. This is just a sketch of a roadmap to a power plant. A detailed roadmap has just been developed by the European fusion community in the recent months, and come to the same conclusion, of course, but with a really dedicated and very detailed roadmap. Well, you can do faster if you want. This is what China is proposing at the moment. China is very aggressive. They took $10 billion. They want to go ahead in parallel to ITER and want to end up with a kind of demonstration that the power plant would work with a machine that is being designed now, and they've planned for first plasma already in 2025. They want to demonstrate 100 gigawatts of fusion power by the end of the century. Well, a fusion power plant would then look like this. You have the plasma inside, so you have the lithium walls, here the blankets where you breed tritium. You heat the plasma, of course, by external means, but then you have kind of, like in all conventional power plants, you cool the walls that are heated up by the neutrons. You go to generators and you go then towards the nets. The net, just a short comparison between fusion and fission. Okay. You have a chain reaction in fission, as you know very well, but the reaction rate in fusion is the very same. You have the fuel for about 2 years operation in fission power plants, 1 gram only for fusion. We don't have radioactive products, and therefore we don't have the problem of meltdowns or unplanned power increases, and we don't need a geological repository, as our materials reduce in activity within the first 100 years to a value that is similar to the coal ash. So finally, if you look at energy modeling scenarios, there are several of that. I just choose one here that at least aims at an increase in temperature by 2 degrees only, and our aim is here to really replace fission power plants to some extent by the end of the century. It doesn't make sense to talk too much about detailed prices. There has been a study led by McKinsey, and in case you have to compete with coal, you will never win, but with renewables, we think we are at the same price, and here you have some pros and cons for fusion. I have mentioned nearly all of them here, and just as a last remark, fusion will be competitive with renewables, but will have very large investments for the power plant, but also in between for the research. Thank you very much.
Thank you very much, Sibylle.